The universe has this hidden blueprint, a structure made of invisible threads. They call it the cosmic web. It's not just decoration, it's this immense scaffold. And it writes the story of every galaxy, our own included. You start to see the night sky differently, not as scattered islands of light, but as one single, flowing masterpiece. This web, it ignited the first stars from nothing, and it explains why some galaxies thrive, while others are stripped barren. Our home is just one thread. In this ancient universal tapestry, that's what it means. That faint pattern we see across the sky, across billions of light years, it started in fire. Before light, before atoms, everything was just energy, a seething ocean, and in that chaos there was a whisper, a tiny imperfection. Quantum physics says even empty space isn't perfectly still. It flickers, and in the first fraction of a second, those random flickers got caught. A cosmic wind took them, a period of expansion called inflation. It's like drawing a tiny squiggle on a deflated balloon. Then you blow that balloon up to the size of the Earth. That squiggle becomes a continent. That's what inflation did. It took those quantum ripples, those spots where a few more particles happened to be, and it stretched them across the whole observable universe. A microscopic hiccup became the largest possible blueprint, the universe's first imprint, a fingerprint pressed into spacetime itself, and from that moment, matter had a map. Gravity isn't a creator, it's a follower. It looked at that map, saw those slightly denser patches, and got to work. For hundreds of thousands of years, the universe was too hot for atoms. A thick fog of charged particles scattering light, but gravity is patient. It pulled gently on those marked regions. A little more mass drifted toward the lines. The dense spots got denser. The empty voids between them grew emptier. That was the quiet work, the foundation, setting the stage before the actors, the stars, the galaxies, could even exist. The destiny of every structure, from the biggest galaxy cluster to our own Milky Way, it wasn't an accident. It was a choice made in the first instant of everything. Written in a language of density and gravity, just waiting for time to translate it into light. Gravity, with just ordinary matter, would have left the universe a haze. A featureless haze. The atoms were made of, the gas in nebulae, the dust of planets. That's all luminous paint. But paint needs a canvas, it needs a frame. And the frame for everything we see is made of something we can't see. It's dark matter, the invisible skeleton of everything. Imagine a vast, dark room. You can't see the walls or the ceiling, but you can see dust motes floating in a beam of light, and you notice something. The dust isn't drifting randomly. It's swirling, gathering into patterns, flowing along invisible currents. You can't see what's guiding it, but you can see its effect. That's dark matter. The unseen architecture that dictates the flow of everything we can see. Scientists think it makes up about 85% of all matter. It doesn't shine. It doesn't absorb light. It doesn't bump into itself or us. Its only language is gravity, and because of that, it was the first to hear the call of those ancient seeds. While normal matter was still a hot, chaotic soup, dark matter was already moving, cold and patient, flowing silently into those marked regions, collapsing into vast, shapeless clouds. Halos, these halos are the true foundation, the gravitational wells, the deep pits in space where everything else eventually falls. Without them, the hydrogen and helium gas from the early universe would have had nothing to cluster around. It would have stayed spread too thin, like mist without a mountain to condense upon. The first stars might have flickered and died out, leaving the cosmos in permanent darkness. Galaxies as we know them might never have been born. So every spiral, every glowing elliptical galaxy we see is just decoration, visible decoration on an immense, invisible structure. Our Milky Way sits inside one of these dark matter halos, a ghostly sphere hundreds of thousands of light years across. We're embedded in it, sailing through its silent ocean. Unaware of its presence except for the grip of its gravity, it's the hidden hand that shaped the cosmic web, drawing the first lines in the dark, long before there was any light to see them by. For a long time, this whole design was just something on a computer, a prediction. People like Jim Peebles did the math, figuring that if dark matter was real and gravity worked the way we thought, then the universe couldn't be random. It had to make a web. They ran simulations on supercomputers, starting with those first seeds and letting gravity do its work for billions of years in the simulation. And on the screens, a pattern showed up: filaments, knots, huge, empty bubbles. It was beautiful, it made sense, but it was all theory, a ghost in the machine. The real problem was finding that ghost in our actual sky. We couldn't see the dark matter threads themselves. So the question was, how do you map something invisible? You look for what it's holding onto. You find the beads on the string. The big change was a shift in how we looked at things, moving from single galaxies to the pattern they all made together. That needed a new kind of astronomy, one that wasn't about studying just one object, but surveying enormous volumes of space. Projects like the Sloan Digital Sky Survey changed it all. They didn't use a single telescope to stare at one spot. They methodically scanned huge parts of the sky, cataloging the positions and distances of millions of galaxies. For the first time, we could build a real three-dimensional map of our part of the universe. And when scientists plotted all those millions of points, the theoretical shadow became real. The galaxies weren't just scattered around like confetti. They were arranged. They traced out these delicate walls and long, winding filaments, coming together at dense nodes where thousands of galaxies swarm. And in between these structures, almost nothing, vast, echoing voids, hundreds of millions of light years across, nearly empty of any bright matter. This was the first real evidence. The cosmic web wasn't just a clever idea. It was the architecture of the cosmos, written right into where the stars are. Every galaxy, from a modest spiral like ours to a brilliant giant at a filament's intersection, is like a bead on an invisible dark matter string. The map showed a design of breathtaking scale and order, a structure so immense it makes single galaxies seem like small details in a huge mural. It confirmed that the universe, on the largest scales, builds with a profound geometry. A geometry that had been hidden, waiting for us to finally see it. Those first maps showed more than a pattern. They showed a system of flow. The web's filaments aren't just lines between points. They're the main highways. The biggest galaxy clusters are like bright cities, and what connects them are rivers, rivers of cold hydrogen gas and dark matter, all moving along these gravitational channels. The force that builds them is gravity. Gravity finds a denser spot where filaments cross a node and it pulls. It pulls everything toward that center. So gas and dark matter from across millions of light years start to drift. They slide down the slopes of the filaments, coming in from all directions. That's the delivery system for the whole universe. A galaxy cluster doesn't just appear, it's fed. It grows by taking in what the filaments bring to it. And that changes a galaxy's destiny. Where a galaxy sits in the web isn't random. It's a life sentence. A galaxy inside a thick, rich filament is like a town on a major river. It gets a constant supply of fuel. That fuel is cold gas, the material for new stars. So those galaxies can keep making stars. They can grow and shine for billions of years. They're the thriving cities, but then think about a galaxy in a quieter place. Maybe it drifted into one of the big voids between filaments. That galaxy is isolated. Stranded, it only has the gas it started with. Once that's used up, star formation stops. Its stars all age together, getting redder and dimmer. It becomes a quiet, older place. Its fate was set not by anything it did, but by its address. The web doesn't just arrange galaxies. It writes the rules. It decides who feasts and who starves, who thrives and who fades, just by controlling the flow of the universe's main resource. The deepest thing about the web isn't what you can see, it's what you can't. You look at a map of the universe and you see the bright spots, the connecting threads. But then you notice the dark parts in between. Those are the voids, the empty places, and they aren't small. They're unbelievably huge. Some of them go on for hundreds of millions of light years. If you put our whole galaxy inside one, it would be like a single grain of sand in a desert the size of a continent. That emptiness isn't a mistake, it's the other side of the story. The web is like a sculpture, and the voids are the empty space that gives the shape its form. They're the deserts that show you where the rivers are. For the web to exist, for those filaments to be so dense, the universe had to make these places of almost nothing. It's called void evacuation. Gravity works like a vacuum, always pulling toward where things are denser. Over billions of years, the pull from the filaments and the nodes has slowly sucked material out of the voids. The thin gas, the dark matter, even a stray galaxy, it all gets pulled toward the edges. It feeds the structures nearby, and that leaves the inside of a void even emptier. A galaxy that ends up there has a unique future. It's isolated, stranded. With no new cold gas coming in from the cosmic highways, it only has the fuel it started with. Star formation just stops. The stars all age together. They get older, redder, quieter. The galaxy becomes a relic, a quiet island in a dark ocean. Its growth didn't end because of something it did. It ended because of where it is. Its address in the emptiest part of the universe decided its fate. So the web shows us a universe of total contrast. Brilliant, connected cities set against a background of deep, defining silence. The voids are the proof of the web's power. They show us the universe's structure isn't just about where it puts things, it's about where it takes them away. The brightest spots on that map, they're also the most dangerous. Where the great filaments cross, they form a node, a gravitational center. That's where the universe builds its biggest things, the galaxy clusters. You can think of a single galaxy as a town. A cluster is a city, a huge, shining metropolis holding hundreds, even thousands of them, all held together by one immense gravitational pull. It's a place of extremes. The space between the galaxies there isn't empty. It's filled with a superheated plasma, gas so hot it glows in X-rays, millions of degrees. Galaxies in there, they don't drift, they scream through that furnace, thousands of kilometers a second, whipped around by all that gravity from all the dark matter and all the stars. For a galaxy, arriving at a node changes everything. It's like moving from a quiet country road onto a superhighway in the middle of a storm. The same forces that built this magnificent city can also break what lives in it. That process is called galaxy harassment. So a spiral galaxy, one full of cool gas and new stars, when it plunges into the cluster's core, it meets a brutal environment. The intense heat from that plasma works like a cosmic blowtorch. It steadily evaporates the galaxy's fuel, the gas it uses to make new stars, and then there are the close encounters. The near misses with other massive galaxies. Their tidal forces can pull at the galaxy violently. They can distort it, strip away its gas and dust in great streams. The spiral's elegant arms get unraveled. Its ability to make new stars gets shut down, sometimes in less than 1 billion years. What's left is something transformed. A red, smooth, elliptical galaxy. Its blue, youthful glow is gone. Its structure is simpler. It's entered a kind of quiet, long retirement, so the node has this profound duality. It's the peak of cosmic construction, where the web's material gathers into the most massive assemblies we know, and yet it's also a galactic graveyard, where the vibrant diversity of spiral galaxies often gets smoothed out. turned into a population of red and dead ellipticals, a galaxy's journey to the heart of the web. It's a story of creation and of transformation, all dictated by the address gravity chose for it. The universe started with construction, a quiet kind of work. Before any stars, there were these halos. Invisible halos of dark matter. The cosmos was smaller then, simpler. The biggest things were these clumps. They were the seeds, the building blocks. And they grew. Gravity pulled them together. Two small halos would drift and merge, like streams becoming a creek. That new, larger halo would attract another. And another. That's hierarchical growth, building from the bottom up, from the smallest pieces to the largest. It's how nature builds complexity, one merger at a time. And as these halos grew, they didn't just appear randomly. They began to feel the pull of the larger blueprint, that ancient imprint from the first moments. They started to line up, to fall into place along invisible contours. Contours of density stretched across the cosmos. They traced lines in the dark. The first faint strands of the web, drawn not in light but in the silent distribution of dark matter. This was the skeleton, taking shape in the cosmic dark. Meanwhile, the ordinary stuff, the hydrogen and helium gas, it had finally cooled down. It was no longer a blinding fog. It could now feel the gentle tug of gravity from those dark matter halos, and it began to move. It flowed along those new gravitational pathways, sliding into the wells the dark matter had prepared. Think of it like water finding grooves in a landscape. The dark matter carved the riverbeds. The gas began to fill them. This was the delivery system turning on. The cosmic web became a channel for the universe's raw material. Within the densest knots, where these early strands intersected, something extraordinary happened. The gas funneled in from all directions, piled up. It became incredibly dense. Under its own weight, it began to collapse. Atoms pressed together. Temperatures soared. And in the hearts of those primordial halos, a new kind of fire was lit. The first nuclear furnaces ignited. The universe's first stars blazed into existence. They weren't like stars today. They were monsters, giants, hundreds of times more massive than our sun, burning ferociously and dying young, in spectacular explosions. But they were the first lights. They lit up the first proto-galaxies, and they did it because the web provided the structure. It gathered the fuel. It created the conditions for that final collapse. The cosmic dawn didn't happen randomly across a void. It happened along the lines of a hidden design. The first threads of the web were the rails on which light itself arrived. That first light had a message in it, a message written in sound, because before the first stars, the universe wasn't silent. It was this roaring sea of plasma, so dense light couldn't get anywhere. It was a fluid, and in a fluid you get waves, sound waves, but these weren't gentle. They were titanic pressure waves driven by gravity and radiation, racing out from every tiny overdensity. Like a stone dropped in a pond, but the pond was the whole cosmos. Those waves traveled for hundreds of thousands of years, until the universe cooled enough for atoms to form. That moment, recombination, was a sudden change. The plasma cleared, the fog lifted, and the waves just froze in place. They left a permanent imprint. A fossilized ring around every one of those original seeds. We see that fossil now as a subtle pattern in the cosmic web. It's called a baryonic acoustic oscillation. A fancy name for a simple idea, a standard ruler etched into space. The waves could only travel so far before the universe changed, so they all stopped at the same distance. That distance became a preferred scale, about 500 million light-years. So if you take a giant map of the universe and measure the distances between millions of galaxies, you find a curious statistical excess. Galaxies are slightly more likely to be separated by that one specific distance than any other. It's as if every node in the web, every great cluster, is surrounded by a faint, ghostly shell. A shell of galaxies marking the outer edge of that ancient sound wave. This is more than an echo. It's one of the most powerful tools in cosmology, because we know the original size of that sound wave from physics. That frozen ring gives us a known measurement. A cosmic ruler of absolute length, and by observing how that ruler appears stretched or compressed at different distances, and thus at different times in the past, we can measure the expansion history of the cosmos with precision. It confirms the grand design we see today. The filaments and voids and clusters grew directly from those tiny quantum seeds. The web isn't just a structure. It's a recording, a phonograph cylinder from the dawn of time, playing back the first notes, now stretched into the vast geometry of everything. That frozen sound wave is just the frame. The picture is painted with light, and that light comes from the gas, the ordinary stuff, hydrogen, helium, the things that make stars and planets and us. This is where the web becomes a flowing system. You have the dark matter as the riverbed carved into space. The baryonic gas is the water. It flows through those channels pulled by gravity, but its journey is more turbulent. This gas doesn't just drift. As it pours out of the empty voids and funnels into the narrow filaments, something happens. It hits a wall. Gas rushing in from one side slams into gas from the opposite side. It's a collision, a universe-scale collision, and like air in front of a jet, this gas gets shock-heated. Its temperature soars to millions of degrees. So hot it becomes a plasma, glowing in X-ray light. For a long time, these filaments were theory. Then X-ray telescopes began to see them, not as strings of galaxies, but as faint rivers of heat, tracing the skeleton we predicted. The web was a map of energy, but within that superheated flow, there's a path to creation. Not all the gas gets caught in the shock. Some of it, in the quieter outer regions, slips through. It stays cold and dense, like a mist in a canyon protected from the sun. This cold gas streams along the filament, a dark current inside a river of fire. It travels for hundreds of millions of light years, and when it reaches a galaxy, it seeps in smoothly, a direct infusion of star-making fuel. Astronomers call these cold flows. A stealth delivery system bringing raw ingredients straight to a galaxy's core. So the web doesn't just deliver gas, it cooks it. It presents galaxies with a menu. A galaxy might get a steady drip of cold flow, forming stars in an orderly way. Another galaxy, plunging into a dense cluster, might be hit by a torrent of hot plasma. That hot gas is useless for stars. It just adds to the galaxy's hot halo or strips the existing cold gas away. The temperature of the delivery decides everything. A smooth, cold flow fosters a grand spiral galaxy, rich with stellar nurseries. A chaotic, hot bombardment can quench star formation, leaving a galaxy red and passive. This is the link, the largest structure, the cosmic web, with its filaments of hot and cold gas, writes the recipe for the smallest structures, the stars. It controls the kitchen. It decides what ingredients arrive and in what state. The blue glow of a young spiral or the red ember of an old elliptical isn't just a choice of the galaxy. It's a signature written by the invisible currents of the web, a receipt for the cosmic delivery it received billions of years ago. The recipe for a spiral galaxy is delicate. It needs a constant rain, a gentle rain, not water but cold hydrogen gas. That's the fuel. It's what keeps the stellar nurseries going, what makes the spiral arms glow blue with young stars. For a long time, astronomers wondered about the supply. How does a galaxy like ours, sitting in this hot plasma halo, keep getting cold fuel? The answer is in the cosmic web. In the simulations, you can see it, not the broad, hot rivers, something more subtle, like underground aquifers. They're the cold streams. Think of the galaxy's halo as a steamy atmosphere. If a gas cloud just fell through randomly, it would get shock-heated, cooked into plasma before it ever reached the disk, but the web gives it a direct line. A protected pipeline. These streams are thin filaments, dense filaments of gas. They travel along the dark matter scaffolding, along the finest local threads of the web. They're so dense they can punch right through the hot halo. They stay cold, shielded by their own mass, and they flow unimpeded. They don't fall, they pour. Straight into the galactic core. It's a cosmic intravenous drip feeding the heart of the galaxy. This mechanism changed everything for the early universe. It explains how the first big galaxies assembled so fast. They weren't just merging in violent collisions. They were being fed by these silent, cold rivers. Gathering fuel from across millions of light years, the web was a root system drawing nourishment from the cosmic soil and delivering it directly. For a spiral galaxy today, its life story is in these flows. If it's still connected to a rich, stable cold stream, it can keep its star formation active. Its spiral arms stay bright. Its disk stays vibrant. But if that connection gets severed, maybe by a gravitational tug from a neighbor, or by moving into a region where the web's filaments are too diffuse, then the fuel line is cut. The galaxy starts consuming its last reserves. Its blue light fades. The star-forming factories shut down one by one, so the majestic spiral we see isn't permanent. It's a moment in a flow, a shape that's only maintained by a constant, invisible current. The stability of our own Milky Way's disk, it seems, depends on a quiet, unseen stream. A thread of cold gas following a dark matter line. It's been flowing for billions of years, keeping the lights on in our corner of the cosmos. That gentle rain isn't everywhere. Some galaxies get it, others face a storm. The web builds nurseries, but it also builds graveyards. The biggest change happens in the busiest places, where the filaments all come together into these dense knots, the galaxy clusters. That's where the web's flow turns harsh. Astronomers have a term, environmental quenching. It's when a galaxy's star-forming life ends, not because of anything it did, but because of the brutal neighborhood it moved into. Think of a spiral galaxy full of cold gas glowing with young blue stars. For billions of years, it's been drifting along a filament like a cosmic highway. But that highway has a destination. It leads right into the heart of a massive cluster, a gravitational metropolis. And when the galaxy plunges in, the environment is completely different. The space between galaxies there isn't empty. It's filled with a superheated plasma, the intracluster medium. It's a fog of gas so hot it glows in X-rays. And the galaxy is racing through this fog at thousands of kilometers per second. The effect is like sticking your hand out of a car window at high speed. The wind pushes back hard. For the galaxy, that wind is the intracluster medium. The pressure is so intense it can blow the galaxy's cold gas clean away. That's ram pressure stripping. It's not gentle. It can be sudden, violent. Imagine a table covered in fine dust. A strong gust of wind blows across it, and the dust is just swept off. That's what happens to the galaxy's star-forming fuel. The gas that was its future gets ripped away, cast out into the hot void, but the assault doesn't stop there. The cluster is crowded, chaotic. As the galaxy screams through, it has repeated close encounters with other massive galaxies. Their gravitational tides pull at it, distort it, further disrupting its structure. The elegant spiral arms, those stable lanes for star formation, get stretched and torn. This galactic harassment adds to the damage. Between the blistering heat of the plasma and the gravitational turmoil, the galaxy's ability to make new stars gets quenched. Efficiently, decisively, the blue glow of youth fades. What's left is a transformed galaxy. Its colors shift to red as the remaining stars age. Its shape often smooths out into a featureless ellipse. It becomes a red and dead galaxy, a passive resident in the cluster core. Its story wasn't written by an internal failure. It was dictated by an address change. By following the web's highway into a place of extreme density, it traded a vibrant, star-forming life for a long, quiet retirement. That's the duality of the design. The same filaments that deliver life, giving cold flows to some galaxies, deliver others into a furnace that strips them bare. A galaxy's fate, its color and shape, is a permanent record of the environment the Web provided. This isn't just a theory, we can see it. You look deep into space and you're looking back in time. Astronomers pointed their telescopes at the most distant galaxy clusters. And they saw something. These ancient clusters from billions of years ago, they looked different. They weren't just red and quiet, they were vibrant. A much higher fraction of blue spirals still forming stars. That discovery has a name, the Butcher-Oemler Effect. It's a direct snapshot, evolution in action. It shows clusters aren't born old, they grow old, and the cosmic web is what ages them. Think of a cluster as a city, a modern city today. It's quiet, established. But a photo from a century ago, during its industrial boom, it was bustling, chaotic, full of new construction, young workers. That's the difference. Distant clusters are those young, bustling metropolises. They're still being built up, new galaxies streaming in along the web's filaments. These incoming galaxies, they're like fresh immigrants. They're rich with cold gas from the cosmic countryside. Glowing blue with young star formation. They've just arrived at the center, but the city changes them. The cluster's environment, that hot plasma, the gravitational chaos, it begins its work. Over hundreds of millions of years, quenching takes hold. The blue spirals, they have their gas stripped away. Their star formation shuts down. They transform into the red, passive ellipticals. The ones that dominate the cluster core today. The Butcher-Oemler Effect is that before and after photo. It captures the moment of arrival. The blue glow of galaxies, freshly delivered by the web before the environment does its work. This tells a story about the web's timeline. It's not a static sculpture, it's a dynamic system. The filaments are conveyor belts, constantly feeding new material into the gravitational nodes. The cluster is the engine processing that material. What we see nearby, the quiet, red clusters, that's just the end result. This process running for over 10 billion years. The supply of fresh spirals mostly consumed, the transformation largely complete. So when we observe a distant, blue-rich cluster, we're seeing the web's machinery in its prime. The delivery and the beginning of the change all in one frame. It's the most compelling evidence. A galaxy's destiny isn't written in its stars, it's written in its address. Within the flowing, evolving architecture of everything, a galaxy's shape tells you where it's been. If you look out into the quiet parts of the universe, the open spaces between the filaments, you see spiral galaxies. Like our own, you also see irregular ones still forming. Those are the calm neighborhoods. Out there, a galaxy can grow a disk. It gets this slow, steady rain of gas. It comes in along one filament usually. That gas settles into a rotating plane. It cools down. New stars form in an orderly way. The spiral arms are like traffic jams, waves that keep going because the fuel is always coming. That beautiful disk comes from a quiet life. It comes from having a steady routine. Then you go toward the city centers, the galaxy clusters, everything changes. The spirals are gone. Now you see elliptical galaxies, smooth, red balls of old stars, and lenticular galaxies which are like disks that faded, their gas gone. This split, this rule, is one of the oldest we know. They call it the Morphology-Density Relation. A galaxy's shape depends on how crowded it is. In the empty fields, you get spirals. In the crowded core, you get ellipticals. That's not an accident, it's a direct result. The environment carves the galaxy. It's like two different ways of building something. Out in the filaments, it's slow, careful. You add one star, then another. You build a stable disk over time. It's about gentle, constant growth, but in the cluster core, it's violent. It's about breaking things and remaking them. When galaxies fall into that dense place, they get their gas ripped away by hot plasma, and they crash into each other. Mergers happen all the time there. When two big spirals merge, their disks are destroyed. The stars get thrown into wild orbits. Gravity eventually pulls all that wreckage into a smooth, round ellipse. All the cold gas gets used up in a huge burst of star formation, or it gets blown away. The new galaxy is left red and dead, so an elliptical isn't a failed spiral. It's what comes after a spiral. It's the product of a violent life in a crowded place. This rule is so strong that just by looking at a galaxy's shape, smooth or spiral, you can guess its address. A smooth ellipse probably lives in a dense cluster. A grand spiral probably lives in a quiet filament or out alone. Their shape is a record, a fossil of what the environment did to them. The spiral tells a story of peaceful feeding. The ellipse tells a story of chaos, collision, and then a long, quiet end. In the universe, your address doesn't just influence you. It shapes you, literally. The web's reach goes all the way to the center of a galaxy. There's something there. Almost every big galaxy has one. Our Milky Way too, a supermassive black hole. Millions or billions of times the mass of our sun. For a long time, we thought of them as in points, just strange objects, but they're not passive, they're active. And what turns them on is the cosmic web. The web is like an irrigation network. It sends gas toward galaxies. Most of that gas becomes stars, but a little bit of it gets diverted. It spirals down like water going down a drain, straight to the central black hole. When that gas falls in, it doesn't just disappear, it gets compressed. Heated to incredible temperatures, it forms a bright, swirling disk of light. That's an active galactic nucleus, it can outshine the whole rest of the galaxy. The energy is almost impossible to grasp, and that energy erupts. The black hole can shoot out huge jets of particles, moving near light speed, stretching thousands of light years. It can drive immense winds of hot gas, blowing outward in every direction. That's where the feedback happens. All that energy blasts into the reservoir of cold gas that was feeding the galaxy. It heats it up, it stirs it violently. It can blow it right out of the galaxy, and in doing that, it puts the brakes on star formation. It's a self-regulating cycle. The web brings the fuel. The black hole consumes some and uses the energy to control how much of the rest gets used. It's a thermostat. If too much gas comes in too fast, the black hole switches on. It becomes active and pushes back. It heats the gas, it disperses it, it slows the galaxy's growth. That feedback loop is crucial. Without it, our simulations of galaxy evolution don't work. The galaxies in the models grow too big, too bright, too fast. They don't match the quiet, red ellipticals we see, or the stable spirals. Only when we include these black hole engines, fueled by the web, do the virtual universes start to look like the real one. So the supermassive black hole isn't a silent king. It's a loud governor. Its activity, triggered by the web's delivery, writes the final rule on how a galaxy lives and ages. The largest structure in the universe and the most compact object their partners. One feeds, the other regulates, a balance written across cosmic time. The story of the web of filaments and flows came from somewhere surprising. It wasn't just telescopes, it was computers. To see the web, we had to build a universe. Inside a machine, these cosmological simulations, they're not animations. They're mathematical experiments. You take a virtual cube of space, billions of light years across. You fill it with particles. Some are dark matter, others are gas. You program in the laws of physics, gravity, the expansion of the universe, the fluid dynamics of gas. Even the basic rules for stars and black holes. Then you press play. You start from a state that matches the cosmic microwave background, and you let it run. 13.8 billion years of cosmic evolution unfolding in months. The results are something else. You see the dark matter particles start to move, responding only to gravity. They drift toward those tiny overdensities, those ancient seeds. They clump, they merge, and from the chaos a pattern emerges: filaments, voids, nodes. A cosmic web woven by calculation. Then the gas particles follow those dark matter channels. They flow in, they shock heat at the dense intersections. They form cold streams along the filaments, and at the nodes they collapse, they ignite. Virtual galaxies are born. Projects like Illustris Tingy and Eagle have done this. They simulate the web and the galaxies inside it, billions of particles tracing the destiny of the cosmos. These simulations are our laboratories. We can run experiments we could never do in reality. What happens if you turn off supermassive black hole feedback? The galaxies in the simulation grow monstrous, too large, too bright, nothing like what we see. What happens if you prevent those cold gas streams? The spiral galaxies don't form right. Their disks are too faint. By tweaking the physics, you see what's essential. You can follow a single virtual galaxy from its birth in an early filament. Watch it migrate along a dark matter highway. See it get shredded by a cluster environment or nurtured by a steady cold flow. You can witness mergers in fast forward. See quenching in action. The simulation connects the grand architecture to the individual life story. It shows the web isn't a static backdrop. It's the engine, a dynamic, flowing engine that processes matter across time. These digital universes have become a mirror that reflects our own cosmos with astonishing accuracy. When you compare the simulated sky to the one mapped by telescopes, the patterns match. The distribution of galaxies, the properties of clusters, the very shapes of the galaxies. They align. That's the ultimate test. It tells us the laws we wrote into the code. The story of dark matter and gravity and gas physics must be fundamentally correct. The cosmic web isn't just something we observe. It's something we can now predict. And in that prediction, you find a deeper kind of understanding. Our simulations are incredibly accurate. Except when you look at the smallest details. We grow a virtual Milky Way from the blueprint of the cosmic web. It should be surrounded by a swarm, hundreds of tiny, dark satellite galaxies orbiting it. But when we look at our actual sky, we only see a few dozen. The rest are missing. That's the missing satellites problem, a quiet gap between our grand theory and our local reality. It suggests the web story has fine print we're still learning to read. The issue isn't that the dark matter halos aren't there. Our models are confident they exist. Thousands of them, tiny gravitational pits scattered around our galaxy. The problem is they're dark. They failed to light up. They didn't become the glowing dwarf galaxies we expected. So what happened to them? The answer seems to lie in the web's earliest chapters. In a period called reionization, after the first stars ignited, their fierce ultraviolet light began to flood the cosmos. That light didn't travel through empty space. It traveled through the web's filaments, the very channels that were funneling gas. That intense radiation acted like a universal heater. It warmed the thin hydrogen gas everywhere. For a massive dark matter halo, this was a minor inconvenience. Its gravity was strong enough to hold onto its gas, to keep it cool and dense enough to eventually form stars. But for the smallest halos, the ones that would become the missing satellites, it was a death sentence. Their gravitational grip was too weak. When the ultraviolet light from the web's first cities hit their meager gas supply, it heated it up. It gave the gas particles enough energy to escape the halo's feeble pull. The fuel simply evaporated before a single star could form. These halos were left as dark matter ghosts, invisible clumps orbiting silently in our galaxy's vast halo. Full of potential but empty of light, there's another, more violent possibility: tidal forces. As these tiny proto-galaxies orbited the growing Milky Way, the repeated gravitational stretching and squeezing from our galaxy's immense mass could have torn them apart. Not in a single cataclysm, but through a slow, relentless process of disintegration. their stars would have been scattered into the faint stellar halo we see around the Milky Way. Leaving no distinct galaxy behind, it's a reminder that the Web doesn't just build, it also filters. It sets a minimum size for success. A galaxy must be born with enough mass, enough gravitational fortitude, to survive both the early universal radiation and the later chaos of its environment. The missing satellites aren't a flaw in the model, they are evidence of this cosmic selection, a signature of the harsh conditions the Web itself helped to create. Our neighborhood is quieter than predicted because the smallest lights were never allowed to switch on. The emptiness around us is not an absence of structure, but a testament to its strict and silent rules. The missing satellites point to something deeper. A piece of the ledger is missing. When you add up all the ordinary matter we can see, the stars, the gas in galaxies, the plasma in clusters, the numbers don't match. Nearly half of it is just gone, unaccounted for. It's a missing inventory, and the main suspect is right there in the Web. They call it the Warm-Hot Intergalactic Medium. The WIM, it's not the cold gas in the filaments, and it's not the blazing hot gas in the cluster cores. It's in between, a huge, diffuse ocean of gas that's been heated. Shock heated to temperatures between 100,000 and 10 million degrees. Because as ordinary matter funneled into the filaments over billions of years, it didn't flow smoothly. It collided. These cosmic traffic jams in the rivers of gas generated immense heat. The energy of that collapse cooked the gas, left it too hot to form stars but too thin and spread out to glow brightly. It's a hidden reservoir, a fog of million-degree plasma filling the spaces between galaxies inside the filaments. Detecting something that faint is a huge challenge. It doesn't shine in visible light, it whispers in two ways. First, it gives off an extremely faint X-ray glow, a signature of its temperature, and second, it leaves fingerprints on light passing through it. When a distant quasar shines across billions of light-years, its light travels through this warm, hot fog. Specific wavelengths get absorbed, wavelengths for highly ionized atoms like oxygen-6 and neon-8. By studying the quasar's spectrum, astronomers see these tiny, specific dips, the shadow of the WIM falling across the light. Mapping this hidden ocean is the final step. To complete the inventory of normal matter, every detection is a point on a map, tracing the finer threads of the Web. This isn't just about finding missing atoms. It's about the complete life cycle of cosmic material. The WIM is a crucial phase in that journey. It's gas that's been processed by the Web, heated by its dynamics. Now it sits in these vast intergalactic conduits. From there, it can cool and flow into galaxies, or it can be blown back out by galactic winds by black hole jets. And rejoin this diffuse reservoir. The WIM is the circulatory system where matter pauses, heats up, and gets ready for its next change. Finding it all means we finally see the full picture of where the atoms that build everything have been hiding. This grand cycle has a side effect. Stars are alchemists. They take hydrogen and helium in their cores and forge heavier things. Carbon, oxygen, iron, the raw material for planets, for life. When a big star goes supernova, or when winds from a galactic core blast out, it's not just energy. They're throwing these new metals into space. They're enriching the gas around them. The galaxy is giving something back, and the cosmic web becomes the channel for that chemical wealth. You can picture a galaxy not as an island, but as a factory on a river. The river is the filament bringing in the raw hydrogen fuel. Inside, the stars process it. They make complex elements, and then the factory exhausts supernova shocks, stellar winds, jets from black holes. It vents that enriched material right back into the river. It doesn't just disappear. The web's gravity holds it. That metal-rich gas gets stirred into the warm-hot medium inside the local filament. It swirls in the galaxy's own extended halo. It becomes part of the reservoir, and then, over hundreds of millions of years, something can happen. That ejected gas, now laced with metals, can cool down. It radiates heat away, loses energy. The gravity from the galaxy or from the filament itself pulls it back. It starts to rain down, a return flow. That's cosmic recycling. The galaxy is reaccreting its own processed waste, but now it's material ready to build rocky planets, complex molecules, new stars that are born already enriched. It's a closed-loop system on a cosmic scale. The web is the plumbing that makes it work, but how efficient this cycle is, that depends entirely on location. A galaxy sitting in a thick, dense filament is like a factory in a deep valley. When it vents its exhaust, the heavy, metal-rich gas tends to stay trapped. It's held in the gravitational bowl of the filament. It churns in the local currents. It has a high chance of cooling and falling back in, or maybe being caught by another galaxy in the same network. The metals are largely kept. They enrich the local group, but a galaxy on the edge of a void, that's a different story. When it expels gas, that material can just blow out into the huge, empty space of the void. There's nothing to hold it, no filament walls to contain it. The gas drifts into that vast nothing, where densities are so low it might never cool enough to clump again. The metals are lost for good. That galaxy and its future generations, they're effectively mining a one-time supply. They can't easily get their heavy elements back. This process leaves a chemical signature in the stars themselves. Astronomers can measure the metallicity, the amount of heavy elements in a star's light. Stars formed recently in a well-connected spiral galaxy like ours, they tend to have higher metallicity. They were born from gas that had been recycled many times, enriched by countless past generations. But stars in isolated dwarf galaxies, or in the outer, quiet halos of big galaxies, they often have much lower metallicity. They formed from gas that had little contact with the rich, circulating flows. Their chemical poverty is a record of their address, a sign they were born far from the web's efficient recycling lanes. So the web does more than deliver fuel and shape galaxies. It governs an economy of matter and metals. It decides which neighborhoods become rich in the elements for complexity, and which stay primordial, simple, and poor. Our own solar system, with its rocky planets and the chemistry for life, it's a product of this billion-year cycle. We are literally made from star dust that was expelled, journeyed through the web, and was gathered back in. Our existence is tied to the efficiency of a local filament, a gravitational channel that kept our ingredients close, cycling them until the conditions were just right. But this whole flowing economy has a deadline because the universe isn't a static stage. It's expanding, and that expansion is speeding up. The force behind that acceleration is dark energy. And dark energy is what writes the final chapter. It works against gravity, the very thing that built the web. As the cosmos stretches faster, the distances between the nodes of the web get larger. The filaments, those rivers of gas and dark matter, they get pulled taut. They become longer, thinner, more tenuous. Think of a network of rubber bands constantly being stretched. They don't snap, but they get so thin that nothing substantial can flow through. The delivery system slows to a crawl. For galaxies, that means the end of easy nourishment. That steady rain of cold gas from the filaments, the fuel for new stars, it becomes a faint drizzle. Then it stops. Galaxies get cut off from their supply lines. They have to live on what's left inside, the gas already in their disks and halos. And as that last fuel gets used up, star formation sputters out. Galaxy by galaxy, the lights start going off. Not with a bang, but a slow, quiet fade. The blue-white glow of young star nurseries becomes rare. Then it's just a memory. The dominant color of the cosmos shifts from blue to red. And then, eventually, to black. The great clusters, those bustling metropolitan centers, they become isolated islands. They drift apart from each other. Their gravitational links stretch too far to matter. The dynamic era of mergers, of galaxies falling into cluster cores and being transformed, it ends. The web freezes. Its structure stays, imprinted on the dark matter and the fading embers of galaxies, but it becomes a fossil. A magnificent fossil, billion light-years wide from a more active age. Over timescales that are almost impossible to grasp, trillions upon trillions of years, the remaining stars burn through their fuel. White dwarfs cool into black dwarfs, neutron stars fade, the universe grows darker and profoundly colder. The cosmic web, which once thrummed with the energy of collapsing gas and newborn stars, goes silent. A ghostly scaffold in an endless, expanding night. That future makes our current epoch look stark and precious. The era we live in right now is the cosmic spring. It's this brief, vibrant period when the web is at its most dynamic, when gas flows freely, when galaxies collide and shine, when stars are born in their trillions. We're living in the golden age of cosmic construction. The web's guiding hand is still active, its rivers are still flowing. Our own galaxy is still being shaped by these currents. To understand the web is to understand that this flourishing, this complexity, it isn't permanent. It's a finite chapter, a glorious one in a story that trends toward stillness. And dark, it makes the intricate tapestry we see today not just a structure, but a moment. A fleeting, brilliant moment in the long, slow breath of the cosmos. This grand vision of a fading web, it all depends on seeing it, and seeing it is the hardest part. To map something so vast, you need more than a single eye. You need a whole symphony of instruments, each one listening to a different part of the cosmic song. The cosmic web is painted in wavelengths our eyes can never see. So we build telescopes that can, optical telescopes like the future Vera C, Rubin Observatory, they're the master surveyors. They'll scan the sky night after night, not to stare at one beautiful object, but to catalog billions of galaxies. Pinpointing their positions with incredible precision, that gives us the most detailed outline yet, the skeleton traced in starlight, but that's just the outline. To see the flesh on the bones, you need to look at the gas. The hot gas in the filaments and clusters, it glows fiercely in X-rays. Observatories like Chandra and XMM Newton, they're our thermal cameras. They detect that faint, million-degree shimmer, revealing where the web's rivers are flowing with superheated plasma. It shows us the energy of the structure. Then there's the cold fuel, the hydrogen gas that hasn't been cooked. It's silent in visible light and X-rays, but it sings in radio waves. Vast arrays of radio telescopes listen for that specific hum, tracing the cold, dark streams that feed galaxies directly. They map the unseen aquifers, but knowing where something is on a flat map isn't enough. You need depth. You need a three-dimensional chart, and that comes from a property of light called redshift. As the universe expands, it stretches the light from distant galaxies, shifting it toward the red end of the spectrum. The farther away the galaxy, the more its light is stretched. By measuring this redshift with exquisite accuracy, instruments like the Dark Energy Spectroscopic Instrument, DESI, they don't just place galaxies on the sky. They place them in cosmic depth. They're building a three-dimensional atlas of the universe, plotting the positions of tens of millions of galaxies. This is the ultimate cartography. It turns the theoretical filaments and voids from a pretty pattern into a measured architecture with known distances and volumes. Each of these tools adds a layer. The optical survey gives us the dots. The redshift measurements stack them into a three-dimensional model. The X-ray vision shows us the hot gas in the lines. The radio ears hear the cold gas in the currents. Together, they're transforming the cosmic web from a beautiful idea sketched in supercomputer simulations into a physical, measurable entity. We're no longer just predicting the scaffold of the cosmos. We're walking its halls, taking its temperature, listening to the flow of its ancient rivers. The final proof of the web's structure doesn't come from light. It comes from the absence of light. To map the cosmic web, you have to trace its gravity. And gravity leaves a mark on the path of light. That's gravitational lensing. The idea is mass curves spacetime. A massive object, a galaxy cluster, it acts like a lens in that curved space. So when light from a distant galaxy travels past that object, its path bends. It gets distorted. For us, the image of that background galaxy is stretched, warped often into faint arcs or multiple images around the foreground cluster. That's strong lensing, a dramatic cosmic mirage. But the cosmic web's filaments, they're immense, but they're diffuse. They don't create those dramatic rings. They cause a subtler effect, weak gravitational lensing. A single filament's pull is too gentle to distort one galaxy's shape. But if you look at millions of background galaxies behind a vast filament, a pattern emerges. Statistically, their shapes are very slightly aligned, stretched in a direction that traces the invisible mass of the filament. The effect is tiny. It's buried in the natural randomness of galaxy shapes. Finding it is like listening for one voice in a roaring stadium. You need enormous amounts of data. You need to average the shapes of countless galaxies to tease out that coherent signal of distortion. That's what projects like the Dark Energy Survey did. They measured the shapes of over 100 million galaxies. They subtracted the noise, and what remained was a map of pure mass, a map of where gravity is strongest. These mass maps, they're breathtaking. They don't show light. They show where matter is concentrated, all matter, and they line up perfectly with the galaxies we see. The luminous galaxies trace the spines of these immense dark matter rivers. For the first time, we could weigh the cosmic web's filaments directly, confirm they hold the vast majority of the universe's matter. Most of it completely dark. It's the most direct evidence we have that the web is real, physical, massive. It's the ghost revealing itself not by shining, but by the way it bends the light of everything behind it. That ghostly imprint we see through gravitational lensing, it had a beginning, a moment it was born. To find that, you look at the oldest photograph, a picture of the infant universe. It's called the cosmic microwave background. This isn't starlight. It's the afterglow of creation itself, released when the cosmos was just 380,000 years old. Before that, the universe was a hot, opaque fog, a plasma so dense light couldn't travel. Then it cooled enough for atoms to form. The fog cleared, and that first light, unleashed in every direction, started its journey. We detect it now as a faint, cold whisper, a microwave radiation bathing the entire sky. It's the ultimate baby picture, and within its subtle texture is the blueprint for everything to come. When scientists first mapped this background with incredible precision, using satellites like Planck, they expected a smooth, uniform glow, a blank canvas. What they found was far more profound. The map isn't perfectly smooth. It's textured with tiny variations in temperature, minute hot spots and cold spots, differing by only a fraction of a degree. These aren't random. They are the cosmic seeds, the very overdensities and underdensities that gravity would later amplify. A slightly warmer patch meant a region with a tiny bit more mass and energy. A cooler patch meant a region with a little less. This was the universe's first unevenness, its first potential for structure. The pattern of these spots isn't chaotic. It follows a specific, predictable statistical signature, a fingerprint of the early universe's physics. Cosmologists can analyze this fingerprint and run the equations of gravity and expansion forward in time. They can predict from this infant map alone how those tiny seeds should grow, how they should pull in dark matter, how they should evolve into the vast network of filaments and voids we observe billions of years later. And when they compare that prediction to the actual three-dimensional maps of galaxies from surveys today, the match is stunning. The distribution of galaxies in the modern web aligns with the pattern of hot and cold spots in that ancient light. The largest structures we see were written into the fabric of reality before the first star ever ignited. The cosmic microwave background is more than a relic. It's the input data, the starting conditions for the greatest simulation of all the real universe. It provides the initial whisper from which gravity composed the symphony of the cosmic web. Every filament, every cluster, every quiet void around us is a direct descendant of a specific fluctuation on that map. We are living in the grown-up version of that infant universe. Our address, our galaxy's place in the grand design, was decided by the temperature of a patch of sky when the cosmos was taking its first breath. That old baby picture has something to say about how we're moving. We aren't stationary. The Milky Way is moving through space very fast, over 600 kilometers each second, more than 2 million kilometers an hour. We don't feel it because everything nearby is moving with us in that same flow. But compared to the cosmic microwave background, that sort of universal rest frame, we are heading toward a particular spot in the sky. This isn't random, it's the direct pull of gravity from the cosmic web. We're being pulled in. The pull is coming from the direction of Centaurus and Norma. For a long time, astronomers knew something huge was there, tugging our local group of galaxies. They called it the Great Attractor. It's not one object. It's a huge concentration of mass, a major gravitational knot where several of the web's big filaments come together. It's like standing in a valley and feeling a wind pulling you toward a distant mountain range. You can't see the peaks clearly, but you feel their collective gravity. That's our situation. The Great Attractor is that mountain range in the cosmos, a dense knot pulling everything in our region toward it. Our view of it is blocked by the dusty plain of our own galaxy, the zone of avoidance, like trying to see a city skyline from behind a foggy hill. For a while, the true nature of it was hidden. But observations in X-rays and infrared light can cut through that dust, and they've shown the scale. The Great Attractor is centered on the Norma cluster, a gathering of thousands of galaxies, but its influence goes much farther. It's the heart of what's called the Laniakea supercluster. Laniakea means immense heaven. It's our home supercluster, a vast web of filaments with maybe 100,000 galaxies, all flowing toward this same gravitational basin. So our motion isn't a trip to one point, it's a migration down a cosmic watershed. We're like a leaf in a river current, flowing along a filament toward a deeper confluence. This journey shapes how we see the universe. When we look out and measure how fast other galaxies are moving away from us because of the universe's expansion, we have to subtract this large, local flow from the Great Attractor first. Our place in the web creates a bias in our perception, a cosmic current we have to account for to see the true expansion. It's a humbling thing. We often think of our galaxy as an island, serene and central. But the truth is we're in motion, swept along by forces on scales so vast they guide entire clusters. Our spiral, with its hundreds of billions of stars, is just a speck in this gravitational river, carried toward a destination we can't fully see yet. Our address isn't a fixed point on a static map. It's a set of coordinates that change with time, tracing a line through the flowing architecture of everything. We aren't just observers of the cosmic web, we are participants riding its currents. Deep in the cosmic web, there are these huge empty bubbles, and inside them you find a different kind of galaxy. Void galaxies, they're like hermits, isolated, drifting in seas of almost nothing. Out in the filaments and clusters, galaxies get shaped by chaos, by collisions. But void galaxies tell a story of solitude. They're often small, sometimes irregular, and they hold onto their gas. They treat it like treasure. There's no one nearby to harass them. No torrent of hot plasma to blast them, so they exist in this state of calm, profound calm. Their evolution isn't dramatic, it's not a saga, it's a slow unfurling. Gentle star formation there, it's not frantic, it's not efficient, it's sporadic, inefficient, but it can be prolonged, remarkably prolonged. A void galaxy isn't being force-fed. No cosmic rivers, but it also isn't being robbed. It just lives off its own savings, its own modest gas reservoir, and it burns through that at its own pace. Unhurried, that makes them valuable, incredibly valuable to astronomers. Studying one is like a controlled experiment in nature. It shows you what a galaxy is like when it's left alone, mostly to its own devices, free from the pressure, the environmental pressure that dominates the crowded web. You can observe its intrinsic properties, how stars form from its own gas, how its structure develops from internal dynamics alone. These isolated systems give you the baseline. They show you the raw version, the unedited version of galaxy evolution, before the cosmic web intervenes, before ram pressure and mergers and harassment rewrite the script. In their quiet simplicity, their gas-rich simplicity, void galaxies hold a key. They show us what every galaxy might have been, if gravity had just placed it in a quieter neighborhood. One extreme is a void galaxy in solitude. The other is almost impossible to grasp. In the web's grand architecture, some filaments are more than rivers. Their continents, the Sloan Great Wall, is the largest known structure of that kind. It's not a literal, solid barrier. It's a staggering filament of galaxies. A concentration so vast it stretches over 1.3 billion light-years. To put that in perspective, traveling at light speed from one end to the other would take longer than Earth has existed. This isn't a single object, it's a titanic alignment. Thousands of galaxy clusters and superclusters, all strung along one immense, curving backbone of the cosmic web. It was discovered by the Sloan Digital Sky Survey, not by looking at one beautiful spot, but by the patient, automated mapping of millions of galaxy positions. That mapping revealed this pattern on a scale that defies intuition. Structures this big are more than record holders, they're profound challenges. They push right up against the theoretical limits. The limits of what gravity should be able to build in the time the universe has existed. Our standard models of cosmic evolution say there's a maximum scale for structure. A statistical limit to how big an overdensity can grow from the tiny seeds in the cosmic microwave background. The Sloan Great Wall brushes against that limit. Its existence asks a quiet, fundamental question. Did the initial conditions of the universe contain a rare, colossal fluctuation we just happened to find? Or does our understanding need a subtle adjustment? Our understanding of gravity or dark energy or the cosmic timeline, it serves as a natural laboratory. Testing the rules of cosmic construction at their most extreme, this great wall is the ultimate expression of the web's gathering power, a filament that won the gravitational lottery. Over billions of years, it drew in matter from an incomprehensible volume of space, funneling galaxies and dark matter along its length into a dense, luminous spine. It is an endpoint, a place where the gentle flow of the cosmic web has created a monument. Studying it is like examining the grandest cathedral to understand the limits of architecture itself. Its scale tells us about the statistical nature of those first quantum whispers. Was the early universe slightly more lumpy in certain places than our best models predict? The wall's immense silhouette, traced in the light of countless galaxies, is a data point from the far edge of possibility. It reminds us the cosmic web is not uniform. It has its quiet deserts and its staggering mountain ranges, and in its greatest peaks we find the clues to the universe's first and most powerful impulses. Even the largest structures can play tricks on our eyes. The cosmic web is so vast, it might be bending our view of something fundamental: how fast the universe is stretching. There's a problem in cosmology right now called the Hubble Tension. It's a disagreement between two of our best ways to measure the expansion rate. One way looks back to the very early universe, to that cosmic microwave background. The patterns in that ancient light let scientists work out what the expansion rate should be today. It's a clean measurement from the beginning. The other way looks much closer to us in time, at supernova in nearby galaxies. These bright explosions work like standard candles, so we can measure distances and get the expansion rate directly in our own era. Both methods are incredibly precise. But they don't match. The local modern measurements show a rate that's faster, not by a lot but enough that it matters. It's a gap that won't go away. So where's the tension coming from? Some cosmologists are pointing to the cosmic web. Their idea is simple but deep. What if our neighborhood isn't typical? The web is lumpy. It has dense threads and huge, empty voids. We know we're in a filament, part of the Laniakea supercluster, moving toward the great attractor. But what if our whole local region, a space maybe 1 billion light-years across, is a little less dense than the universe's average? Think of trying to measure the slope of a huge landscape, but you're standing in a valley. Your reading of the overall incline could be off because you're in a dip. If our cosmic address is in an underdense region, a gentle void on a giant scale, it could change how we measure expansion locally. The gravity from all that missing mass around us would slightly shift the motion of nearby galaxies. It might make the local expansion rate look different from the true global average. So the Hubble tension might not be a mistake in our physics. It might be a correction for our address. To really understand the universe's expansion, one of the most basic numbers in science, we might first need to map the invisible scaffold we're inside. The cosmic web isn't just a spectacle. It could be the key to solving a modern mystery. It reminds us that our view of the cosmos is always framed by where we are in its design. The quiet void galaxy and the immense Great Wall, they're two ends of a spectrum, but most galaxies, they're in the middle. They're in motion, following the currents of the web. And that motion, it often leads to a meeting. The cosmic web, it's the choreographer for the most dramatic events. Collisions, mergers, these aren't accidents. They're orchestrated by the same gravitational flows that bring the gas. As galaxies travel along filaments toward the great nodes, their paths are set. They're on converging courses. It's like traffic flowing into a city from several highways. The cars are destined to meet at the interchanges. In the cosmos, those interchanges are the dense intersections of the web. The galaxies are the cars moving on gravitational rails they can't leave. When two galaxies meet, the outcome depends on speed and angle, and that's dictated by their place in the web's architecture. In the dense core of a massive cluster, galaxies are screaming past each other, thousands of kilometers per second. These are high-speed encounters, like two cars on a freeway, passing close but too fast to truly connect. They might sideswipe each other gravitationally. That's harassment. It pulls out long streams of gas and stars, causes damage, but they don't merge. They're moving too fast to become one. But out in the quieter suburbs, in the smaller groups along the filaments themselves, the dynamics are different. Here, the relative speeds are much lower. A few galaxies, having fallen into the same gravitational well within a filament, they orbit each other, a slow, stately dance. Over hundreds of millions of years, their orbits decay. They spiral inward, and finally they embrace. That's a true merger. A slow, majestic, transformative collision. When two spiral galaxies of similar size merge, it's one of the most energetic events. Their beautiful disks are the first things to go. As they intertwine, their structures are destroyed by immense tidal forces. The orderly rotation of stars gets scrambled into a chaotic, swelling ball. But within that chaos, there's creation. All the cold gas from both galaxies gets violently compressed. It triggers an explosive wave of new star formation, a starburst so intense it can briefly outshine the rest of the galaxy. For a short, brilliant period, the merger glows with the blue light of newborn stars, and the supermassive black holes at the hearts of both galaxies, they are also fed. As gas is driven toward the new center, the black holes feast. They light up as brilliant active galactic nuclei. Eventually, the two black holes themselves will spiral together and merge, sending ripples through space-time gravitational waves. The end product of all this is something new, a large, smooth, elliptical galaxy. The elegant spirals are gone, replaced by a redder, rounder, quieter system. The merger has used up the gas, quenched the star formation, retired the galaxy. The web sets the schedule. It determines which galaxies are on a collision course and how fast they'll meet. By controlling the traffic flow, it decides when and where these upheavals happen. The majestic ellipticals in cluster cores, the tangled, star-bursting galaxies we catch merging in deep field images, they're not random. They're the direct result of deliveries and meetings scheduled billions of years ago. Written into the flowing script of the cosmic web, a galaxy's past written in its stars often tells the story of a long-ago merger, a merger that its position in the web made inevitable. That first light wasn't just a signal, it was a fire, and it changed the chemistry of everything. For hundreds of millions of years after things began, the universe was filled with this fog. A fog of neutral hydrogen, atoms with their electrons still attached, and that fog absorbed the ultraviolet light from the first stars. It kept everything in a kind of twilight. But then more of those massive stars ignited, and the first black holes started feeding, and they sent out a flood of radiation, ultraviolet and X-rays. This radiation had the energy to strip electrons away from the hydrogen atoms, to ionize them one by one, and then in waves the fog started to clear. That was the epoch of reionization, the universe waking up from its dark ages. But this awakening, it didn't happen uniformly. It followed a map, the map of the young cosmic web. The first stars and galaxies, they didn't light up randomly. They ignited in the densest knots, where the filaments of the web crossed and funneled the most gas. These knots became the first cities of light, and from these cities radiation began to pour out. It streamed along the very filaments that had delivered the gas. Think of it like a forest fire, but spreading along pre-cut trails. The ultraviolet radiation traveled down the dark matter channels, ionizing the hydrogen inside them. It created bubbles, expanding bubbles of clear, ionized space with brilliant galaxies at their centers. Over time, these bubbles grew. They began to touch, to overlap, until eventually the bubbles from all the early nodes merged together. The last pockets of neutral fog were burned away. The universe became transparent. Like it is now, this whole process took hundreds of millions of years, and its progress was dictated by the web's architecture. Where the web was dense with filaments and nodes, reionization happened early. It was fast. In the vast, empty voids between the threads, it happened late, or not at all, until the bubbles finally expanded into those deserts. This interplay had a consequence. A profound one. It created a filter for the next generation of galaxies. Those small, dark matter halos, the missing satellites, they were forming at the same time out in the thinner filaments. On the outskirts, when the wave of ultraviolet radiation from the big cities finally reached them, it heated their scant gas supply. For a small halo, that heat was a death sentence. Its weak gravity couldn't hold onto the energized gas. The fuel for future stars just evaporated, went back into the intergalactic medium. These halos were still there, full of dark matter, but they were stillborn. They never got a chance to shine. So the cosmic web didn't just guide where the first lights turned on. It also guided the shadow they cast. It decided which smaller seeds would be sterilized by the coming dawn, and now we're on the verge of watching this. Telescopes like the James Webb Space Telescope are built to look back to this exact time, to see the faint, red-shifted glow of those first bubble walls. To catch the galaxies inside them in the act of clearing the fog, by mapping these first lights and the shadows they create, we'll see the infant cosmic web. Not as a theory, but as a living, breathing system. A system where architecture and energy first learned to dance and set the rules for everything that came after. A star lives alone, but it doesn't die alone. When a massive star runs out of fuel, it doesn't just fade, it explodes, a supernova, and that explosion can outshine a whole galaxy. In that violence, everything it made gets thrown out. Carbon, oxygen, silicon, iron, the stuff for planets, for oceans, for life, it's all blasted into space. But that's just the start. The shock wave from that supernova pushes it. So do the winds from other massive stars. It pushes this enriched material out. It mixes with the galaxy's halo of gas, and then something bigger happens. When the supermassive black hole at the center of a galaxy feeds, it doesn't just make light. It drives colossal winds. These are like galactic exhaust systems. They take metal-rich gas from the very heart of the galaxy and propel it out, far beyond the galaxy's visible borders. At speeds that approach a fraction of light speed, that's how a galaxy exhales. It breathes out the chemical residue of generations of stars. But where does it all go? It doesn't vanish. It enters the rivers, the cosmic web. These outflows inject the metal-polluted gas right into the filaments, the warm-hot intergalactic medium that surrounds galaxies. It's like a factory on a riverbank, venting glittering dust into the current. The river carries it away, mixes it with the clean water from upstream. That's the web's role. It's the distribution network. The filaments are blending channels. The pristine, primordial hydrogen and helium gas, flowing since the dawn of time, now meets this ejected exhaust from living galaxies. They swirl together in vast million-degree flows. Over billions of years, this mixing is relentless. The entire filamentary network changes, from the densest nodes to the most tenuous strands. It becomes chemically enriched. It's no longer the pure soup of the early universe. It's a complex broth, seasoned with the ashes of dead stars, and that has a consequence. For any galaxy that forms later, or for any existing galaxy that's still pulling in gas, the fuel it draws from the web isn't pristine anymore. It arrives pre-polluted. It has a higher metallicity from the start. A new galaxy forming from this gas gets a head start. Its first stars will already have traces of heavy elements. That changes everything about how those stars form and evolve. It dramatically increases the potential for rocky planets around them. Our own solar system is a product of this. This billion-year recycling program, the iron in our blood, the calcium in our bones, the oxygen we breathe, every atom heavier than hydrogen and helium was cooked in a star that died before our sun was born. That material was expelled. It journeyed through the web's filaments, mixed with other flows, and was eventually gathered back in by the gravity of the young Milky Way. We are not just stardust, we are stardust that has traveled the cosmic highways. The life cycle of a single star in a galaxy you might never see is connected to the chemical foundation of a planet a billion light-years away. All because the web's currents act as the circulatory system, distributing the products of stellar alchemy, weaving the chemistry of life into the fabric of space itself. Our galaxy isn't alone. It's part of a neighborhood, a local structure. That's the local sheet. It's a huge, flat plane of galaxies, like a pane of glass. And in this sheet, you have the main galaxies, the Milky Way, Andromeda, Triangulum, dozens of smaller dwarf galaxies, all moving within this same thin plane. It's a kind of galactic suburb bound by gravity, but this sheet isn't random. It's a piece of the cosmic web. It's our local filament seen right here. The sheet is the visible part of a dark matter thread, a riverbed where our galaxies have gathered, and this filament goes far beyond our group. It's a gravitational highway. One end links to our nearest giant neighbor, the Virgo cluster. That's over 1,000 galaxies, about 54 million light-years away. The other end points toward that huge pull we feel, the Great Attractor. Our local sheet and everything in it is sliding along this channel. We're moving on a path set billions of years ago. This local filament is our piece of the universe. By looking at it, we see how the web's machinery works up close. We can watch the traffic, measure the flows, see the future in the slow dance of galaxies. And that future has a major event. The Andromeda Galaxy and the Milky Way are on a collision course. They're not just neighbors, they're in a gravitational embrace that started when their dark matter halos touched. They're falling toward each other along this local filament. In about 4.5 billion years, they'll meet. It'll be a slow merger. Their spiral arms will stretch out into tidal tails of stars and gas. Their cores will merge into one giant elliptical galaxy. This isn't a disaster, it's a natural step, a result of sharing the same filament. The fate of our galaxy isn't just its own story. It's about our place in the local web. Every measurement of our motion, every prediction of that merger, confirms the pull of this larger structure. The local sheet is like a classroom. It shows how filaments guide galaxies, how they set them on converging paths, how they dictate the timeline for events over billions of years. By understanding our own filament, we have a template. A key to reading the connections between distant galaxies in other filaments. Our home is a detailed specimen. It shows the intimate mechanics of the grand design. The maps we have now, they're just a first draft. The next generation of cosmic cartography is already happening, and it's going to see the cosmic web with a clarity we can only picture today. This isn't about one new telescope. It's about a synchronized fleet of instruments. Each one is designed to map a different layer of the universe's architecture. The European Space Agency's Euclid mission is a dark universe detective. It won't stare at single objects. It will scan over a third of the sky. It will measure the shapes and redshifts of billions of galaxies. Its primary goal is to create the most extensive three-dimensional map of the cosmic web ever made. It uses weak gravitational lensing to trace the distribution of both dark and ordinary matter. And it will watch how the web's structure has stretched and evolved over 10 billion years. That will give us our best measurement yet of dark energy's influence. Meanwhile, NASA's Nancy Grace Roman Space Telescope will perform a similar, immense survey, but with a different emphasis. Its wide-field instrument will peer back to the universe's adolescence. It will capture the light of galaxies as the web was still actively assembling. Roman will find millions of galaxies through gravitational lensing, but it will also discover thousands of new exoplanets. And study the infrared sky. Its deep, wide surveys will help us understand how the web's environment influenced galaxy growth, that peak era of star formation. On the ground, a revolution of a different kind is being built. The square-kilometer array, the SCAR, it isn't a single dish. It will be a vast network of radio antennas spread across continents. Its superpower is listening. It will detect the faint radio hum of neutral hydrogen gas, the fuel for stars across the cosmos. This will allow it to map the cosmic web not by the galaxies that light up, but by the cold, dark rivers of gas that flow between them. It will trace the web's skeleton in its primordial fuel, revealing filaments that are too faint in starlight to see. Together, these projects will do more than add detail. They will create a living movie of the universe's large-scale structure. We will watch filaments grow and merge over cosmic time. We will see voids expand as dark energy accelerates the universe's expansion. We will measure the subtle tug of dark matter on the web's geometry with unprecedented precision. This flood of data will likely reveal structures even grander than the Sloan Great Wall, or new, unexpected patterns in the distribution of matter. It will test our fundamental theories. Does Einstein's gravity hold perfectly across these vast, empty voids? Does dark energy behave as a simple constant, or does its strength change over time? The cosmic web, mapped in such detail, becomes the ultimate laboratory for these questions. We are moving from an era of discovery to an era of precision. The web will transform from a beautiful, theoretical framework into a measured, physical entity. Every filament, every node, every void will have a known mass, a known temperature, a known history. This isn't just about filling in a map. It's about reading the fine print on the universe's blueprint, written in gravity, dark matter, and dark energy, to finally understand the full story of how everything fits together. The realization of this immense scaffold changes everything. It changes our cosmic address. Our existence isn't a random accident in a chaotic void. We are the result of a specific process, a guided process. It began with quantum ripples in the first instant. It was channeled by dark matter rivers. It culminated in a spiral galaxy built along a quiet filament. The atoms in our bodies were forged in stars. They were delivered and recycled by these same currents. We are not just in the universe, we are of its architecture. Every person, every tree, every mountain on Earth is made from material that journeyed along the threads of the cosmic web. This idea of connection isn't a metaphor, it's physical, it's gravitational and chemical. The same invisible forces that arrange galaxies a billion light-years away also hold our planet in orbit. Gently, the universe operates as a single system, an interconnected system. A change in the density of a filament millions of years ago could have altered the flow of gas to our galaxy. It could have changed the very star our planet formed around. Our local reality is woven into the largest tapestry imaginable. This challenges a deep-seated human intuition. The intuition that the cosmos is a vast, empty, and random place. The web reveals a profound order, an elegant order, an order that doesn't care about our daily lives, but one that nonetheless provided the precise conditions for our galaxy to emerge, for our solar system, for our planet. We find ourselves in a universe that builds with intention. It follows a blueprint written into its first light, a blueprint for complexity, for structure, and ultimately for the possibility of observers who can look back, who can trace the threads and wonder at their own place within the design. This perspective is humbling and it's empowering. We are unimaginably small. Yet we are participants in a story of cosmic construction, a story that spans all of time and space. Our ability to map the web, to understand our origins within it, is perhaps the universe's way of comprehending its own structure. Its own magnificent structure. The cosmic web is about connection. It connects the earliest quantum moments to the spiral of our own galaxy. It shows a universe that isn't separate islands, but one flowing system. A dynamic tapestry where every thread, every knot, every empty space is part of a grand design. We've traced its lines from the frozen imprint in the ancient afterglow to the brilliant clusters where galaxies change. We've followed the cold streams that feed spirals and felt the hot winds that stop them. This invisible architecture, woven from dark matter and traced by gravity, is the true author of the cosmic story. It wrote the rules for where light would first appear. It built the highways that deliver star fuel, and it set the schedule for the slow-motion collisions that reshape galaxies. Our place in this web isn't accidental. The Milky Way spins inside a local filament, a specific thread in the fabric. The atoms in our world were forged in stars that lived and died because this web gathered the ingredients. Those atoms were distributed by its currents and then gathered back in by our galaxy's gravity. We are literally children of this structure. Our ability to look up and decipher this web might be one of its most remarkable outcomes. With tools like radio dishes listening for cold hydrogen and space telescopes weighing dark matter through lensing, we're doing a kind of cosmic archaeology. We're reading the universe's history from its architecture. Each new map, each deeper survey adds another chapter. The future promises more clarity. Missions like Euclid and the Roman Space Telescope will chart the web's evolution across 10 billion years. The square-kilometer array will listen to the dark rivers of primordial gas. We'll watch the web's response to dark energy's push, seeing how the largest structures change over time. This isn't just about filling in a picture. It's about understanding the fundamental forces that shaped everything we see and are. The cosmic web shows a universe of profound order and breathtaking beauty. An order on scales so vast they humble our daily concerns, yet it's linked to our existence. It teaches that we aren't just spectators in a random cosmos. We are participants in an immense, ongoing construction, a single thread conscious of its place within the greatest structure of all.